Hi, Michael Milligan. I'm a scientific computing consultant with the Minnesota Supercomputing Institute, that's at the University of Minnesota. And I'm here to try to shed some empirical light on how are scientists using Python on supercomputing environments. So first I want to say a few words about us. Minnesota Supercomputing Institute, we are established as a statewide computing facility. We are part of the University of Minnesota, and the vast bulk of our users come from the University of Minnesota. But we have reach out into other institutions, even some corporate environments within the state of Minnesota. All told, we have 3,000 to 4,000 active users at any given time, coming from in the vicinity of 1,000 different research groups, which you can do the math, means our median research group size is about 3. In terms of resources, we have a couple of clusters. All told, order of 25,000 cores. In addition, we have other resources. We have visualization labs that we run. We have storage. We're up to 5 or 6 petabytes. We operate heterogeneous systems of GPUs. We operate Hadoop clusters. It's really a mixed bag. And the same is true on the HR side. So in terms of the staff we have, we are not just sysadmins. We are also consultants, like myself, working with researchers who come in. We teach workshops, tutorials, and we also have people doing original research within our walls, such as they are. And I say all this to emphasize, first, what we are not. We are not a national lab. We are not aiming to be or compete with the facilities with million-core top 10 supercomputing facilities. What we are, if I had to summarize it in one line, is an organization that serves the long tail of computing research. We have many, many researchers in a staggering variety of fields doing a mind-boggling variety of things. And I think this makes us a really interesting observatory from which to try to sample what is the scientific community broadly doing in this ecosystem. So I said I want to bring some empirical data, some objective measures to the floor. So let's start with what we all know. And I'm going to say know with really big scare quotes. We know that Python is popular. How do we know that? Within the context of the MSI, we know that because, well, okay, we have Python tutorials, and they're very well attended. We have Python training materials on our website, and we can look at our logs and say, yep, people are accessing those a lot. We look at our ticketing system and say, yep, we get a lot of help tickets requesting help with, this, that, or the other Python package, or hi, can you install this thing for me? And we see those coming in. And of course, we have people on staff like myself who are constantly running around saying, hey, Python is awesome, you should use it. Which, of course, people then take by inference to mean that, yes, people must want to use Python. But these are all fairly subjective. And I want to emphasize that from sort of a starting baseline, there's nothing I've said here applies just to Python. This is sort of the level of knowledge we have about most software packages, most software ecosystems at an environment like ours. So if you want to get a bit more specific, well, first of all, let's ask, is it worth putting in the work to get more specific? Do we care? My argument is the answer is emphatically yes. Yes, we care. If we don't have information about what people are doing, then we have no idea what to support. What do we optimize? What emerging trends do we need to take our time to learn about? What facilities that we offer are being underused and we need to advertise better? And it's also the case that sort of from a perspective standpoint, if you're working from these subjective measures, you're really just catching the squeaky wheels, in my opinion. when you have a help ticket coming in, that's a problem that has already bitten and already hurt the research program of at least one user. Consultant experience, you go around and ask people like me, say, hey, is Python awesome? I say, yes, Python's awesome. That's reflecting problems that I've already solved, questions that I've already answered. That's, again, not a forward-looking measure. And as far as our users go, we could ask our users, hey, what would you like to see work better? But in practice, users are terrible judges of this. They'll tell you, oh, we'd like X to work better, but that has almost no correlation to whether actually X doesn't work at all right now, and you should have known this ages ago, versus X actually is working really, really well, and the user's just being picky. The user has no idea. So then, why study Python? Why do this report and bring it to this conference? Well, Python, being both a programming language and an ecosystem, has a really diverse and really diffuse user base. I mean, just look at this conference. You've got people from all over the scientific disciplines here, and that's true of our users as well. You've also got many different styles of use. I don't think I'll get any dispute here that it's currently a topic of interest. So I think everyone in this room can say, yes, we know people are using Python. You're all using Python. Furthermore, Python actually can be a good topic to study precisely because it forces us to do better, forces us to get better at measuring what our users are doing, because it's not a proprietary software package. It doesn't have a license server you can query. I can't go and say, oh, how many users checked out the license for this feature. There's no equivalent thing in Python. There's no single binary to implement, to instrument. You can run Python from many locations. People might be running their own Python scripts. We have several different installs of Python, and that's not even counting the various Pythons that are embedded in other software packages that aren't themselves Python, but have Python as an add-on, have Python libraries, have Python bindings. And additionally, our users can run Python on their own without even telling us. They can, download Anaconda and run it in their home directory, and we don't know. So if we're looking for objective measures, this is going to depend very much on what your starting point is. So in our case, we're a supercomputing institute, so a lot of the work that's being done on our systems is going through some kind of batch scheduler. So that already gives us a leg up. So pieces of information we have. Well, we have job logs. Users compose scripts to submit to the batch scheduler, and those scripts launch some jobs. So we have access to those scripts. Environment module actions. So this often happens at computing institutes. If you want to use, say, Python version 3.4, you have to type some special command to load it in your path. In our case, it's module load Python /3.4. So we can put instrumentation on that module load command because we provide that. Scheduler logs. We have to bill people for the CPU time they use. We record, how long did your job run, how much memory did it use, where did it run, how many nodes did it run on. So these are all pieces of information that we have access to. And for tying it all together, in our case, we're going to be using Splunk, which, I'm sorry, isn't Python, but it actually plays really nicely with Python. And so we're just using that as log file analysis. You could, in principle, do this with anything that can chew through log files. So let's start putting this together and just do some really simple queries. So to start with, okay, so anything we can get a job ID for, I can get runtimes for. So let's try querying all those job scripts for people who used the word Python or mentioned a something.py file in their job script. How much CPU time was consumed? Well, so I'm only going back one quarter because we're still in the process of deploying these various monitoring tools. So Getting consistent data more than 3 months back is still problematic, but we're working on it. And if you see here, in June, we had something like 9 CPU years of execution time for jobs meeting these keywords. You'll also notice it's really, really variable. I don't think that Python uptake was drastically greater in June versus April. So, why is it that we have 10 times greater usage in June? Well, there's also the question of matching. This is already incomplete, we know, because say I didn't put in a keyword for chime, that's Python. I didn't put in a keyword for pymol, that's Python. I didn't put in a keyword for RPY2. So there's a bunch of packages that we're not tracking here, but let's go with this for the time being and see where it takes us. Another thing I can do is count versions. So I have job IDs. I can look at what modules they loaded, and I come up with the versions of Python that our users are loading. It's interesting to note that the vast majority of our users actually don't care what version of Python they get. Maybe they should. They're just typing module load Python and hoping for the best. One of these days we may switch that to Python 3, and maybe they'll be surprised. Maybe they won't care. It'll be an interesting experiment someday, but I'll do it on a slow day. And otherwise, you can see it's a mishmash of versions. Actually, the second most used thing is Neuron. That's a Neuron simulating package that has a Python scripting facility attached to it. But then after that, it's all versions of Python, some that we compiled, some EPDs coming from InThought. There's probably one coming from Anaconda in there too. Sadly, mostly Python 2. And this doesn't even count the virtual environments that our users are putting together. So that is one downside of a long tail. It gets hard to migrate users off old versions. Each of those old versions, they're showing up in that list because they're being used enough to be in the top 10 versions that are being used. And we have more below that we're trying to call. So another thing we can do is look at the node specification people are asking for. So the notation here is the first number is the number of nodes, the number of physical servers that your job's running on. The number after that is the number of cores per node that you're asking for. And people sometimes ask for some odd number of cores because they actually need that many cores. Other times they just ask for the full number of cores on a node so they know that they have that node to themselves and they have the full memory bandwidth and whatnot. We don't really have any way of measuring how many of those cores are they actually using, but we do know what they're asking for. And so looking at this chart, I would say, are they running Python in parallel? Yes, absolutely, good. This is a nice use of supercomputing resources. Except, well, then you start digging into the data. So, for example, this is the data for June, and in June, a single group submitted hundreds of Neuron jobs, which represents 80% of the CPU time on this plot. And again, Neuron has Python as a scripting interface. We don't even know if they were using that, so this may or may not actually count as a use of Python. And then you'll notice here, there's a group that was requesting nodes that have 2 GPUs. That's because this is also a single group that's making those requests. They're running WHOMD. It's a molecular modeling code that uses PyCUDA. So we know they're using our GPUs, so that's good at least. And not even showing up on this graph, if you do this by CPU time, you find that the number 3 group is a group using MPI for Pi and sklearn on 2 to 5 nodes each. So maybe the right thing to do is to split this up by group. And I'm getting flagged, so I'm going to go through this a little bit quickly. So we do that, and this is, again, the June data. If you could do other months, the distribution is like, 80, 10, 5 kind of distribution is going to be about the same, but you get different groups. Because in our environment, groups are popping up all the time. The group is Johnson M that's using 80% of the time this month doesn't even show up in May. What do the group names mean? Well, this is where it gets kind of tedious and manual. So I dig into the logs, I look at the actual scripts they're running. I look at the actual Python scripts they're running underneath that, and I can classify them. Say, okay, well, Johnson M is that group that's running Neuron all the time. Not as far as I can tell using the Python features. The other groups, 3 of them are doing genomic analysis of various sorts of BioPython. One of them's doing cosmology with MPI and SciPy. And one of them is doing, like, reptile phylogenetics. So, cool. So, BioPython, text munging, MPI, SciPy, scikit-learn. Those are definitely being heavily used, and we can actually see that in our data. But that was kind of tedious and manual. Maybe the thing to do is just ask our users. Well, yes, we tried that. We sent out a survey to users that pop up as heavy users in these kinds of data collections, and the response rate is poor. They're definitely enthusiastic in many cases, but we just don't have enough of them to say much. So there are next steps. One of the biggest questions is, can we wire Python to automatically tell us what's being run? The answer, not really yet, but do check out the video of the telemetry BOF on Wednesday, because they're thinking about that exact question. Thanks. Yeah, so the question was about how to run jobs that can, in principle, be run in parallel, but they're all really small. So, right. Yeah, so I would agree with you that getting 1,000 cores for 10 minutes on most clusters is going to be kind of a pain, because you're going to wind up waiting 10 minutes or longer to actually get that reservation. But if you could run it on, say, 100 cores and use something to treat that as a sequence of jobs of dependencies. So like Dask, for example, was presented had a really nice presentation on Wednesday showing how they can break up a task into an array of jobs, and Dask will automatically figure out, okay, all of these need to run before this step runs, and then all of these things need to run, and spread it over however many chunks you have. So it's targeted at multi-threaded applications, but there is a Dask distributed that may work with QSub. I'm hoping to look more into that today, actually. Yes?
A little bit about how, so you had 9 years of Python in June.
Right.
So what fraction of that is of your capacity is that? It's a little arithmetic, and it looks like you have about 2,000 CPU years a month. That's 25,000 cores divided by 12.
Right.
So is it really 9 versus 2,000? It seems likely to me that you're missing a lot of data.
Yeah, I wouldn't be surprised if I'm missing a lot of data. On the other hand, we already know that easily 50% of our capacity is being used by people with like big legacy apps, computational chemistry and whatnot, that need very little interaction from us and don't need modern technologies. They just need CPUs that they can compile their code on and run.
Thank you.
Thanks.